Greetings, this is Artie from Artifact Electronics. In this episode, we'll be looking at this vintage James Bond briefcase. Now, what might this contain? An assortment of lethal items, such as poison pens, ICBMs, or people that text while they drive? Well, let's open it up and find out. Latch number 1. Alright, too late to turn back. And it is. Well, that's kind of boring. Not really, but I had to say that after the build-up. Yes, it's a tube tester. It's a B&K Dynaquick Model 700 Dynamic Mutual Conductance Tube Tester. And you may remember that I did an episode on a Hickok TV3 tube tester a few episodes ago, and now I got another one. So some may say, isn't it enough that you're hoarding oscilloscopes? You need to hoard tube testers too. And no, that's not really true. And I will actually come up with a legitimate excuse for having gotten this tester. Alright then, here's the culprit. This is a plug-in from a Tektronix 561A oscilloscope mainframe, circa early 60s. This is the vertical quad trace plug-in, a type 3A74, and if we have a look at its interior, we can see that this was a hybrid design. Hybrid in that you can see the regular vacuum tubes on the left, and those I could test in the Hickok tester. Bunch of transistors over here, which I could test with my snazzy transistor device tester, which I unfortunately blew up a few weeks ago, so I kind of had to test those, which just the multimeter and the diode junction test. That's not very exact, but at least it will tell you if there are any junction shorts or opens in there. And that's good enough for now. But then I had a problem with these guys, figuring out what kind of transistors were they. And if we look at this, this is what it looks like. Let's see if we can get this to focus at all. It's a little bit better over here. But it's got an odd arrangement of pins on the back. And the reason I had a hard time figuring out what this did was it's not a transistor at all. It's a vacuum tube. And I should have known because it is actually called a Nuvistor. And Nuvistor is emblazoned across the case, but I thought that was a manufacturer's name. It isn't. It's the type of device. Nuvistors were invented by RCA in the late 50s, and they're described as a thimble-sized vacuum tube. Now, the timeline is a little bit strange, considering that William Shockley invented the modern transistor in 1951. He originally called it the sandwich transistor, but it was officially released as the junction transistor. And that was 8 years before the Nuvistor came out. But I guess the two people hung on to what they had and tried to push their technology forward. It's obviously a very compact tube made entirely of metal and ceramic. Needs specialized manufacturing equipment to make this thing and evacuate the air from it. I don't think they're static sensitive, so we should be good there. But I guess they were trying to push their technology ahead of solid state. Probably not a wise decision, but when you had champions like Tektronix who used that part, that gave credence to that technology. Now I think that the most famous device that used a Nuvistor was the Neumann U47 studio microphone, which is the holy grail for any studio. Supposedly the best sounding microphone ever made. And the original tube that was used in that Neumann microphone, which was a Telefunken VF14, was discontinued, but somebody figured out a way to use the Nuvistor in its place with slight circuit modifications. So I guess that means there'll always be a market for these. But other than that, the fact exists that this particular plugin used the Nuvistor and I need to test it. Now the Hickok tester listed this. It's a model 7586 tube, but in order to test this I needed a socket adapter because of the strange pinout on it. And that socket adapter, I guess I searched for it, it wasn't readily available, and after a while I gave up because I really didn't want to sink any more time or money into the Hickok tester. When I found the B&K tester, I read through the docs. Before I actually found it, I read through the docs, and I found that it lists this guy in its list of supported tubes, but also it doesn't need an adapter. It actually has a socket that directly accepts this and tests it. So the whole thing became a no-brainer for me to, instead of further investing in the Hickok tester, to invest in an entirely new and more modern tester to be able to test these initially, but to make the whole testing process for other tubes a little bit easier and streamlined. Getting back to the tester, I found this one locally, and thanks to eBay I had to pay more than $10 for it. I was assured that the tester was in perfect working condition, and well, it was clean, which means, well, at least somebody had dusted it off before I went there. It's in pretty good shape. Still has the original tube chart in the lid, which just gives you the settings. And one of the nice features of this is, remember it had the words Dynaquick in its name, and the Dynaquick part refers to the upper portion of this, where there are, 34, 35, 36 sockets, and these sockets have the names of the tubes that they'll test right next to them, and also the sensitivity adjustment. You only have to plug the tube into the right socket, adjust the sensitivity socket, and then look at the oversized meter to tell you what shape the tube is in. But they also give you the switch section down here, and that is more like the Hickok tester in that you have to set up the switches, and so in this case the sockets aren't labeled as far as what tubes are concerned, but you look that up in the tube chart, set it up, and press the test buttons, and it shows you the state of the tube. Another good feature of this is this: on the Hickok, if you had something with two sections in it, you could test one section, and then you had to reset all of the switches to be able to test the second section. This one's actually smart enough to be aware that there's some tubes with two sections, and once you have this set up, you can either press the test 1 or the test 2 button to check both sections of a tube. Now the best plan of attack for this for me was, even though I was assured that it was in full working condition, I figured two things I need to do. One is there's a short calibration procedure for it, and I figure if I can adjust it to the proper specs, it should be functional. But as a second step, I will use some tubes that I have previously checked in the Hickok tester and that actually have proven themselves in working equipment to see how those work. And if those two steps, if it passes those two steps, I think we can assume that it's good and start testing the Nuvistors. And this is the magic socket right over here. Now, in order to test this, you need to make some connections to socket number 1 over here. And what you will need is a tube test adapter socket, which I was lucky enough to find. And this is what it looks like. It plugs into a socket, has another socket on top, but also contacts on the side for you to be able to clip on test leads. So that thing goes in here, and since we're looking at the top of the tube, pin 1 is this over here, which you can't see. Pin 1 is over here, and basically goes in a counterclockwise direction to pin 7 over here. Now, this test adapter is kind of a forerunner to the IC test clips that looked like this, that basically clipped onto an IC and then gave you these pins to hook up your test equipment to, logic analyzers, logic probes, or whatever. It is this guy's very useful because of sticking wires into the tube sockets and getting a good connection proved to be somewhat difficult and unreliable, but with this guy in place, everything should be a snap. One important part I left out is when you're setting this up for a tube test, not only do you have to adjust the sensitivity as noted next to the tube numbers, but you also have to set the heater voltage, and that's easy to do. Because the heater voltage is identified by the first digit in the tube designator, or the tube model, I should say. So a 6AU5, you set it to 6. 3C2, you set it to 3. With that out of the way, let's start with the calibration. The first calibration step is called the short sensitivity adjustment. And what we do here is we set up the short indicator bulb. We adjust that, and the way you do it is you connect a 1 mega ohm resistor between pins 2 and 4, and then you press the shorts button, and you observe the shorts lamp. So when I press it, you can see it comes on. Can we adjust it? Yes, till it just turns off, and then we're supposed to bring it back so it just turns on. Don't know if you can see it, but it just off, on. There you go. That completes the first calibration step. The second calibration step is the grid emission sensitivity adjustment. For that, we hook up 20 mega ohms between pins 1 and 6. I used 2 10s because I didn't have a 20, and use the pot accessible through socket 33 to adjust the grid emission so that the meter goes to 20, and with the glare you probably can't see it, but 20 is right over here. So when I press the grid emission, it goes a little bit above 20, and all we got to do is adjust it in the right direction. The meter doesn't have a mirror scale, so it's a little bit harder to adjust to look at it right from the top and put a shadow there, but come on. And there it is, exactly at 20. Alright. Calibration step number 3 is the signal voltage adjustment. For that, we measure the AC voltage pins 1 to 2 on the test socket. And what we need to do is adjust the voltage to 1.5 volts AC. Now, with no test button pressed, we're getting a voltage that is pretty high compared to what we're supposed to adjust it to. And what I figured out finally is it's the same problem I had with the Hickok tester, and that is this expects a VTVM and a 10 meg meter. A meter with 10 megs input impedance doesn't provide it with any load. This expects a load. On the Hickok I used a 100 kilo ohm resistor to shunt the meter, I think, but that still gave pretty high voltage readings in idle without any button pressed. I came to the conclusion that this one needed a 10K resistor. So if we clip on a 10K resistor, we end up with a few millivolts, and in order to test the signal voltage, we press test button 1, and without me even having to stick the screwdriver into socket number 25, we have reached our 1.5 volt AC. And again, that's right on. So in order to reach pot R11, I had to take it out, put it on its side, and R11 is here. No more convenient access through a tube socket. But pressing the test 1 button still gives us the 2.3 something reading, and let's adjust this to the prescribed 2.5, and there you go. For the final calibration step, this is the balance control adjustment. We have to adjust R5. R5 is also not conveniently located, but rather it's over here. And they want us to hook up a 6K 10 watt resistor from pin 5 to pin 2 over here. And in socket 1, set the sensitivity control to 100 and adjust R5. And that's what I did, except on my first run I cheated, and I used a pot like this, which I adjusted to 6K, and as I was doing the adjustment it started to smoke. So they weren't kidding about the 10 watts. So I actually put a 20 watt 6K in there and did the adjustment while I was leaning over it to watch the meter. The meter has to come exactly to 0. When the test button is pressed, I was obscuring the camera, so I can't show you that, but basically I was staring at the meter, pressing the button, and then turning this pot till the meter was zeroed. Heed the instructions. They're not kidding about the 10 watt resistor over here. Looks like the calibration went well. It really wasn't that far out of calibration, and that seems to be a good indicator that this is functional. One more thing I like to do is to check the actual heater voltages generated on here, and let's have a quick look at the schematics here. The heater voltages are derived from this multi-tapped secondary winding on the transformer. And this is a selector switch, and it simply routes the appropriate voltage to the heater pins of the tube under test. So the way I'm going to measure this is I put the test socket back in. One of the tubes tested in this socket is a 6CB6. I looked up the data for that and found that the heater is on pins 3 and 4, and connected that to the multimeter, which is set to AC volts. So now we'll turn this guy on, and we have it set to 1 volt. Now, first thing we do is check it against the schematics, which lists that tap as 1.18 volts. We're getting 1.28, but since we are measuring this without a load, it is expected for the voltage to be high. I mean, this isn't even that high. It's only about, just under 10% higher than specified, so this voltage is good. So I'm not going to go through every voltage. Let's, even though when you're doing the testing you probably should go through every one, but for the sake of brevity I will just jump around. Let's go to 6 volts, which is listed in the schematics as the 6.15. Now we know that's supposed to be 6.3, but the schematic says 6.15, and it's a little high, but that one's good. The next one is the 12 volt tap. The 12 volt tap is interesting because when I showed you the transformer, there's actually more selections available on this switch than there are taps on the transformer. So some of the settings actually share the same tap. That's the case here. The 12, 14, and 15 setting all share the same tap on the transformer, which is marked as 12 volts. We are getting 13.4, which is a little higher than 10% off. So that one's good too. The 25 and 30 also share a tap, which is listed at 27.9, and that shows up as 29.6. Again, in the range of 10% higher, and if we go to 30, that voltage should stay the same because it's the same tap, and it does. And finally we go to the highest, which is 50, and 50 listed on the schematic and shows up slightly over 10% higher than spec'd. So it looks like the heater voltages are good. And keep in mind, it's important to check that, because if the heater voltages come out too low, the tube's not going to perform very well, and if the heater voltage is too high, you're going to damage, if not burn out, the heater coil. So this is a good test to do. Well, let's do some real tests. I have a pair of 1287s. They're military spec. They're supposed to be brand new, and I've tested them on my other tester, and they tested as very good. Let's see what this one says. So let's set things up. Heater voltage is 12, socket is number 8, and sensitivity is supposed to be 74. So let's power it up. Let's give it some time to heat up and see what this says. And this should probably be enough time. So we press, well, of course we're supposed to press the shorts button first to see if it lights up. The grid emissions, which should stay at 0, otherwise it's bad. So that's also good. Test 1 gives us a reading of approximately 93. And the second section tests as 105. So that matches up with what I read on the other tube tester. So that tube is definitely good and is being tested good on here. So now let's take its sibling here, and again let it heat up a little bit. We can start with the shorts test, the grid emissions test, and test 1. Yeah, this one is higher than the first section in the last tube. This one shows us about 95. And section 2, wow, that almost pegs the meter. That's like 112. Again, that matches with the former results I read, so those tubes are good. Now let's have a look at some known bad or weak tubes here. Here's a 6J6 that goes into socket number 2. The heater has to be set to 6 and the sensitivity to 60. So I'll give it some time, check for shorts. What do you know? Well, that's interesting. It gave us a short, but now that it's warmed up, it doesn't. Grid emissions are at 0. This only has a single section. Let's try the short one more time, because you're not supposed to test it if it shows a short, but it doesn't anymore. And that's maybe because it was cold. Well, test 1 doesn't show anything. So this tube is completely dead. And that matches with my former test. And what else do we have? The 12AU7. That again goes into this slot. Heater's 12. And the sensitivity 56. No short. No grid emissions. This is a 2-section tube. Test 1. Yeah, it's still rising, but let it heat up a little more. But no. This is squarely in the replace area. Test 2, the second section. Oh, it's the same. So, yep. This tube, both sections identically weak. And again, this matches with what I measured before. So I think we can give the tester a clean bill of health and continue with the real reason why I got this guy. Here's the original array of the 7586 tubes. So to get, what I'm going to do is pull them one by one, test them, and then put them back so we know exactly which one was tested. And for this test, let's just define this as having 4 rows of 2 columns each of these, and we will pull them and test them in a row order. So we're going to do this, this, then this, this, and so on. So now we got the tester set up for the 7586 tube. That one is specified at a 6-volt heater voltage, 65 on the sensitivity scale. And this one uses the so-called switch section down here as opposed to the Dyna test or the quick test section. In this section there are several sockets that are not labeled with tubes, but rather you have to set these switches to do a proper tube test. Another difference is that you don't have to specifically test for shorts. On this section the meter will deflect without any of the buttons pressed if there is a short in the tube. So let's turn this on. We have the tube from that comes from the position row 1 column 1, which is channel 1 in the vertical amplifier. There are no shorts. We'll give it a little bit of time to warm up, and it's beginning to warm up, and we press our test, and it's in the questionable area, definitely weak. Alright, let's have a look at the row 1 column 2 tube. Nothing bad happening here. It's still increasing, still warming up. Needs a little bit more time. And this one's at the lower end of the questionable area. So that one's weak too. I checked all of the tubes. They all showed up as weak. They all landed in the yellow questionable area. Here's the last one, row 4, column 2, and this one. Oh, it just barely makes it up there, but then swings back. So this one's also weak. Of course, you know, this tube tester is magic, because as expected, if we test it, we have the proper bias voltage set over here, but if we mess with the bias voltage, the tube becomes good. But going back to the prescribed setting puts it back into the yellow area. So every single one of these tubes tested as weak. So the results were consistent. Every single tube showed up as weak. Still makes me a little bit suspicious, especially after, you know, you play with the bias voltage and they jump into the good area. But the tester was set up exactly as described, and we have it calibrated, so I think those tubes are actually weak. One explanation, of course, is that this the scope it comes out of is an early 60s Tektronix, which was probably on 24/7 for many, many years, and that would describe all of these tubes degrading in a consistent manner. Another thing that allays my suspicion a little bit is the symptoms the scope exhibited, and those were that every time I turned the scope on, and there are 4 traces, randomly 1 or 2 of the traces would exhibit noise, a lot of noise riding on the traces. Then I would power cycle the scope, not quickly, but rather letting it cool down for 5 or 10 minutes, turn it on, let it sit for another 5 or 10 minutes to have the tubes come up, and I would see the same thing, that again a random 1 or 2 traces would show noise, and they would always be different than the last time I observed it. The second thing I observed doing that kind of power cycling was that let's say I had the traces set to ground and I had them all positioned vertically to be one major division apart on the screen. After doing a lengthy power cycle, they would lose their position. Some would be in the same position, but most of them would land in a completely different vertical position. And this again was random every time I power cycled the scope. I think these tubes showing up as weak could possibly explain that. Now, I haven't put a lot of time into the Tektronix. I have briefly measured voltages, checked capacitors, and even though the capacitors were a little high, things seem to be in spec pretty much on that scope. But what I'm saying is I'm going to have to spend more time on the scope and actually see what sort of bias voltage it supplies to the to those tubes, and what effect it would have if I temporarily increase the bias voltage, and see if that fixes the problems I observed. Well, to sum it up, I now have a tube tester that's a little bit easier to use than the first one, the Hickok. A little more modern, supports more tubes. Most important though, this may have saved me from a fool's errand on the Tektronix scope trying to look for problems where the problem could have been, or probably is, the bad 7586 tubes. Now, I checked on eBay, 7586s cost about $10 at the lower end and go up from there. So, 8 of those with shipping would quickly approach $100. So, what I'm saying is if it does turn out to be the tubes that are bad, it probably isn't worth it for me to fix that up, because putting the new tubes in may start revealing other problems, and the scope may become a money pit. Now, that doesn't mean I'm going to give up on it. I will go and spend some time on the scope. But I do think that our main subject today, which is this tester, most likely saved me a lot of fruitless searching. Anyway, I hope you enjoyed this. The magic tube tester will probably come in very handy in my future exploits with tube-based equipment. So don't forget, if it deserves a thumbs up, then by all means give it one. And if you haven't subscribed, go ahead and do so, because obviously one thing we're going to be looking at in the future is some tube-based oscilloscopes, and it's not only going to be the tech. Take it easy.